spend too much time on this. I think it's more interesting to actually discuss a specific example of spectrum sharing in radar bands, which we have studied in the past couple of years. And you can find actually the results of this work published in a conference, in an IEEE conference focusing on dynamic spectrum access. It's called DISPAN. It's the main conference of IEEE dealing with issues related to cognitive radio, DSA, spectrum sharing. So for those of you that are doing research in a cognitive radio related domain, it's well, if you don't know it, I recommend to have a look into the DISPAN proceedings and possibly to submit your work there, because that's the community you want to get in touch with. Okay, there are of course general conferences like ICC, GlobeCom and so on, VTC, but this is very specific in terms of cognitive radio, dynamic spectrum access, spectrum sharing. So for those of you interested in that area or that are doing work in that area, it's a conference worth considering. And definitely, if you check in the proceedings of this conference, you will see a lot of related works to what you are doing or planning to do. Okay. As we discussed before, in general, at least to the standards, for the standards we are used to in cellular systems, the spectrum used by radar systems is sort of underutilized, right? They don't use it in all regional space, which implies also duty cycle is small, so there are many possibilities to share it. Now this part of the course focuses on the technological aspects, and then I will stop, I'll move on to some other topics. So but you know, there are of course many considerations of a political nature, right? Policy nature, safety nature. I'm not touching upon those, right? I'm constraining myself to discuss a technical solution for spectrum sharing. The other issues are important, but they are not within my domain of expertise. I just flag that there are other issues and they should be considered as well. So as we discussed earlier, there are two ways to do spectrum sharing, not just with radars but in general. There is a way to do spectrum sharing which is of a spatial nature. So for example, it simply means that if you have a certain primary system, now this is true even if you don't have a radar, it's always true. So you have you define an exclusion zone. For example, fixed satellite systems services work based on this concept of exclusion zones, FSS. It's not just a radar thing. Okay, and so within the exclusion zone, potentially, I mean, ideally, you should not transmit as a secondary, right? You're not allowed. So you do have your own cell, your own coverage area outside, and the intersection between the exclusion zone and your own coverage should be ideally an empty set, right? You don't want to enter with your transmission within the exclusion zone. Now, the problem with this approach is that it is not a very smart approach. It's very static. Okay, so it might be still okay if you have a primary system which is transmitting in an omnidirectional fashion, right? You kind of transmit around the transmitter point in a certain, within a certain radius. So it's kind of, you know, omnidirectional. But radars don't work that way. The radars are directional. Okay. So they do transmit in a certain direction, and then this direction actually moves with time, right? It can be circular or sectorial, doesn't matter. But and actually, I was discussing with a student before in this class, and he was rightly mentioning that there is also the third dimension, which we don't consider in this work. So in this work, we consider only the azimuth angle. So right, basically a certain two-dimensional space, but of course you have also the elevation angle, right? You can change the elevation, the tilt, right, of the transmitter. Therefore, if you transmit like very high up, then it would impact little, right, the ground, or you know, vice versa. It might impact just, you know, a certain specific portion of the area if you have this inclination, right? It depends on how you tilt your antenna. So in this case, we don't consider that. We just consider a two-dimensional scenario. As a related note, an interesting area of work which is picking up, it's what is called 3D beamforming. Again, traditionally beamforming, as far as I'm aware, and most of the wireless network modeling has been two-dimensional, right? You consider a surface. Now the truth is that's a simplification, because you have, in a country, of course, you have hilly regions, and in a city you have tall buildings, right? So it's not that all users are at the ground floor, or at the z equal 0 meter level. So it might be interesting for those of you that are working on beamforming or related subjects to look into this 3D beamforming, because it's picking up as a topic. And for those of you that are interested in deployment, deployment planning tools, like these network planning tools and so on, again, I think there is scope to do work in in three-dimensional space. So to deploy a network not only with considering, say, an XY plane, but also a Z plane, right? So when you see, for example, the work we saw also yesterday with Professor Da Silva on stochastic geometry, you see a surface, right? The truth is, especially in some scenarios, that's not the case, right? You have also the third dimension. So just as a related note, you might consider also the third dimension in your work. Okay, so what happens is that the transmission is directional and it changes with time. So, for example, if the radar is transmitting in this direction, you strictly speaking don't need to be outside of the exclusion zone, because the intended receiver is here and there is no overlap whatsoever with your cell. So why not using it for your own transmission? So that's what we call temporal sharing. Okay. There are a couple of works here in this part of the course which I'm going to present. Both were published in this IEEE DISPAN conference. One has more to do with temporal sharing, and another one we are going to see what happens if you use beamforming actually in the secondary system. Okay, so now it's not a completely new topic of research, as I was mentioning this morning, because there have been attempts already to share the radar bands with commercial systems. An example is Wi-Fi in 5 GHz, where they basically are sharing some part of the radar band using what is called DFS, dynamic frequency selection, which is a fairly inefficient scheme and also not that dynamic as far as I'm aware. And there were problems in the sense that they were kind of underestimating the possibility of interfering radar. So I think there has been issues, as far as I'm aware, with dynamic frequency selection. So there is a need for something better. The FCC in US have recommended the sharing of 3.5 GHz band with small cells in the LTE context. And I mean, also given the problems that Wi-Fi is experiencing, it might be a good idea to actually replace Wi-Fi in this band, at least to some extent, with femtocells of an LTE nature, where you can actually do a better spectrum sharing. So one of the reasons behind the interest of researchers in sharing radar bands is actually this FCC recommendation. So there are different types of radars operating in any band, and what is the threshold that you should adopt, and what is the sensing time that you should adopt. So I don't believe that DFS is that adaptive in this sense. Okay, so in general you should have a scheme that picks the right threshold and the right sensing time depending on the radar. Okay, so I don't have time here in this course to go too deep on that, but we do have research working on similar issues. Okay, so identifying the right amount of time you should spend for sensing and the right threshold. This is going to be a bit more basic scenario I'm going to talk about today. And definitely there is no temporal sharing for DFS. So the current operation of Wi-Fi system in 5 GHz band is completely based on exclusion zones. Okay, so there is nothing that takes into account the directionality of radars. So if the radar is pointing towards another direction, you would not exploit that. So that's how we identified this problem, and we started to study it. I got a question before. I'll see what I can do about that, but about hints how to, especially for the junior people in this room, how you start research, how you find the word, a problem worthwhile your time and the time of the other researchers. And I think well, there is no silver bullet. Okay, there are many factors. I'll see if I can accommodate a lecture next week about this, like more general research philosophy kind of thing, if you like. There is interest. If there is no interest, then fine. Okay, you let me know. Okay, if you are interested in that. So one way to identify research problems is to look exactly for this kind of gaps, right? Things that have not been considered, or have been considered only to some extent, or models that you don't believe are very realistic. Okay, so clearly, if you have a system sharing the spectrum with the radar, and you know that temporal sharing is a good idea, and the system is not doing it, then you should try to investigate yourself what happens if you do it. Things like that. So you have to look into the papers and see the assumptions and try to challenge the assumptions. Another good source of inspiration is the future work section in papers, because they tell you what they couldn't do or they're planning to do. And that's normally something where you could start to look into yourself. Okay, just as a couple of tips to do how to do research. So there is actually, in general, what we call a required exclusion zone. Now I don't exactly recollect where we got these numbers, probably from the specs of the radar operation. So you basically, the required exclusion zone, that might be to do with this DFS, I think, and Wi-Fi. So you basically, it's defined by a received power of -34 dBm. Okay, and now the discrepancy is evident with what basically DFS assumes as an exclusion zone, which is much more conservative, -64 dBm. Okay, and even worse still is that the real exclusion zone is not even this circle here. It's this strange keyhole shape almost, right? So you have, like, of course, some area close to the radar, and then you have the sector which is illuminated by the radar at any time. So there is definitely a huge gap between what's really needed, in a sense, for the operation of the radar and what the regulation imposes on the system. So there is a lot of wastage in terms of spectrum opportunities. So that's, in a sense, the motivation of the work. You see, another thing is that there is a kind of discrepancy between the rotation period and the sensing time. It's sort of a bit slow. On the other hand, to be absolutely sure of the pattern, you might have to wait a few sweeps of the radar. So there is a trade-off between acquiring enough information to draw some conclusion and being quick, right? You want to use the spectrum quickly, especially if you have an LTE system. So an LTE system would work on a 1 millisecond basis, right? So you have the scheduling frame for LTE is 1 millisecond, right? That's the TTI. So every millisecond potentially should reallocate your resources, your frequencies to the users, right? So there is definitely, between a minute and a millisecond, there is quite a bit of gap, right? So you want to do things also quicker if possible. Okay, so very kind of comic-like description of the problem. So SU stands for secondary user. So in this case, it's our, say, LTE system or mobile network system. And then you have the geolocation database, okay, which contains some information about the primary system. And then the secondary would would basically query the database, saying, okay, I'm in a certain location, operating a certain band, transmitting at certain power, any problem with any PU in the area, any radar in this case in the area. So the database would, you know, start to basically do this exercise of intersecting your coverage zone based on the bandwidth, so not based on the frequency you operate at, right, and based on the power and on your position. So it would draw, in a sense, another area, and then it would intersect with the exclusion zone, and it would tell you whether there is intersection or not. If there is an intersection, then you're in trouble. You should hold off, right? You should not transmit. If the intersection is an empty set, then you're good. Okay, then basically once you say are sure you can transmit, there are some parameters that can be you can know of, like depending on where you are, depending on the certain radar system and where it is, you will have a certain threshold to commit to, okay, before you interfere. Intra pulse modulation thing this means, and then antennas scan period. Okay, there are a few parameters. So this is more to do with the modulation used by the radar, and then this is more to do with the actual basically behavior in time of the radar emissions. And there are others. Okay. So based on this, it would tell you where and when you can transmit. Okay, so there is a match between your like the secondary characteristics and the radar characteristics in this case, and then the database would recommend something. Now we say database aids sensing because there is also a component of sensing. So we don't just rely on database, but we also do some sensing in this case. So we combine the two. A reason to do the sensing is that it can give more information. I mean, it can give information with a finer granularity. Okay, you can basically, when you access a database, the database is updated not so often, at least less often than the time scale you are operating at as a secondary system. So you have to refine these measurements possibly with sensing, which you can operate at a quicker pace. Okay, and another thing, it's the fact that the pixels based on which the database is defined are normally sort of big. Okay, but you can actually have your own sensors in the same area and refine the information. So it might be that the database tells you in this squared like this, in this square, say with a side of 200 meters, you cannot transmit at all, but maybe your sensors will tell you, okay, maybe in a quarter of this area you can, something like that. Okay, so you try to combine the two things. Any questions so far? Nope. There are more details in the paper. Okay, so if you're interested in that. So there are a few actually things you should do to come up with a good estimate of the radar activity as a secondary system. So first of all, you have to detect the pulse. You have to realize there is a radar transmitting, right? You have to basically identify that there is an actual radar transmitting in the area. You might actually because since there might be more than one radar transmitting, you are going to group together the pulses that look alike. That's what is called clustering. That's a classification problem. So you're going to group the different candidate, say, radars. You're still not sure whether they are radars or not, into different clusters. Eventually you refine things further with a time of arrival, the interleaving, and once this is done, which is called pulse sorting. Okay, so hopefully at the end of this pulse sorting block, you will have an idea of how many radars you have. Okay, and what you have to do next is to basically identify the beam and the scan pattern. So how does the radiation pattern looks like, and how does it behave over time? So there is another block of the system that would do that, and eventually you look up in the database and try to see the match. Okay, so there are some templates in the database with which you would compare your understanding of the radar. Okay. So, for example, in terms of the pulse detection, what you could do is to measure the power you receive over time, and then say, for example, at some point you start to see a behavior like this. This is a clear indication that there is something like radar transmission going on, right? Because there is clearly a regularity in the received power, and it peaks at regular intervals, which means with some period you will be hit in a sense by the transmission of the main beam of the radar, right? Yeah, I think that's the main message here. Okay, now going back to the architecture, once you have detected the actual radar presence, you will go into sorting the pulses. And you would what we call de-interleave the detected pulses into different pulse trains, PT, based on few parameters, okay, that have to do with the radar operation: the carrier frequency, the pulse width, okay, so how long in time the pulse is actually on, right? Intra-pulse modulation, that is kind of a heavy assumption. It implies that you have some collaboration from the radar system, okay, because that is a bit more to do with the waveform design of the radar signal. And then pulse repetition frequency, or also called interval, is simply the period, okay, of the perceived pulse. So how much time between two different occurrences of a certain radar pulse. Okay, so what you do with some machinery, I won't go into the details of, you basically separate the pulse trains, depending on different characteristics, and then you come up with candidate pulse trains. Okay, so you have, for example, the first pulse train here and the second pulse train here. Again, the details are in the paper. Okay. Any questions so far? No? Yes.
So why are you interested in pulse sorting? Why are you doing pulse sorting?
Because what you get is something like this.
We are interested to know whether there is radar transmission or not.
Correct.
So why are if
Yeah.
if we detect the energy?
Yes. No, you're right. But the point is, you don't just want to be aware there is something. You want to use that opportunity. So that's what I'm saying here. For example, different radars will have different protection requirements. For example, they're not all alike. Okay, I'm not an expert in radar systems, but my understanding of radars is that they're all very different. Okay, some are more sensitive, so they want to be protected more. Some are less. And beside that, if you want to use basically the spectrum opportunity in a better way, you have to have an idea how this shape is, and that depends on the radar system. Okay, so you have to identify which radar are we talking about. Is it a circular radar? Is it a radar that just operates in a sector? So if you identify, for example, that PT1 belongs to a sectorial radar, why do you care about the rest? You see, so you're right. If your goal is just to sense, you don't need this. You are fine with the pulse detection stage. But if you want also to make some use of it, then you need the sorting. Yeah. You need to know with whom you're dealing, basically. And that's the problem with the Wi-Fi version of sharing the radar band, because they are really not doing the smart things. Okay.
Can't we do it from database only? Because is it that these types of radars will change with time?
You do need some, yes. I mean, database definitely is a main tool, right? That's why we say database aided. I mean, definitely it's good that you have a database because you can store a lot of templates for the different radar systems, operating parameters. I think, for example, I mean, one reason to do sensing is to refine this information over time and space, right? To become more precise. Another reason, I'm not going to touch it here, is some new work we are currently doing. It's also to synchronize with the radar. So at some point there might be, any system with time tends to desynchronize, as you know, right? You might be synchronized at some time, but then, with hardware impairments, glitches of any kind, misalignment of local oscillators, I don't know, you name it, mobility with Doppler, right? So anything tends to bring you outside of the synchronization situation. So you do need to probably resynchronize with the radar, and for that you need to do some sensing also, right? You need to basically, it's something that the database won't tell you. The database is kind of passive, right? But you have to have an active role, for example, to enable synchronization. So, or to identify, now this is more advanced than what we are doing here, but to identify, for example, opportunities of transmission. Okay, so to, like what we call interruption periods, where you should just, be silent and so on. So to be very precise with these periods, you have to have an integration of the database information with sensing. Database alone will only go that far. Okay. All these parameters, like pulse width, pulse repetition frequency, the carrier of the radar transmission, can either be estimated. That's what we call limited support by the database. So, for example, if you have a database that is not willing to share with you that much, then even more you need the sensing to be helping you. Okay, so for example, you could just have some ideas about a range for PW. The database, because of security, because they don't want to give you all the information, they tell you, okay, PW is between X and Y. Then you have to do sensing to really understand how, you see. So what the database would do would basically give you the initial condition. But then the sensing would kind of refine the thing. So in the parameter estimation, that's probably the best example for the need of sensing. Now, if you have a database which is very generous and gives you everything, including the waveform, then maybe sensing has a more limited scope. But we are trying to be general. So depending also on the willingness of the radar system to collaborate, you might have a larger or smaller role of sensing.
Which of these parameters are mapped to the type of radar?
I think all of them. All of them. Probably the most.
Carrier frequency, how carrier frequency is related to how radar is moving, whether it is circular or sectorial?
It is not only the single carrier what you're saying, it is something called modulation. I mean, there's FM also.
Yeah.
So you get to know about what is the band of this pulse width. It's not simply 1 over PW. So there will be multiple frequencies which will be inside.
Right. I think that
Spreading will be also there if they are using Barker
right.
codes. Then again, it's a different thing altogether.
I think, like, what my understanding is that probably one of the most telling features is this IPM, is intra-pulse modulation. So it's like, and that's probably the one that is most difficult to get hold of, because you would really understand a lot of how they transmit. I mean, that's what we assume normally as not readily available, but again, this is general. Okay, so if there is a framework where the government is very supportive and they're very open, then you can share much more, okay, information. You can get many more details from the database, but otherwise it's also true, to the extent that maybe you could also do only sensing, right? But the problem with only sensing approaches has been there also in cognitive radio. I mean, I do remember when people were saying you don't need anything else than sensing. It doesn't work, okay? So you do have to provide the sensitivity requirements, you know, that are legally acceptable. You do need database support, and you do need it not only for sharing the radar bands, you do need it in general. Now the trend is very much database and sensing, not either or, but both, okay? Beaconing, I'm honestly not seeing it going many places, but database and sensing together, yes. Okay. Now, there are more parameters also. So if you look at our papers, the framework is general, okay, and we did consider a few. Of course, this is our understanding of the radar systems. None of us is working in the radar system business, so this could easily be improved and refined, you know, talking with radar people. I absolutely agree with that, but I think to some extent we are taking reasonable assumptions based on literature and what we are understanding, okay, but again, this could change, could be improved. Okay, now the last thing you do once you are fairly sure who you're dealing with and how many of them, right, which is what you get out of detection and sorting, you do the last bit, which is beam and scan analysis. So you do try to understand the antenna radiation pattern, and you do try to understand the antenna scan pattern, okay? Sorry, the antenna scan period, okay? And you do have this practically a detection problem. So you do have a certain metric, okay? You build sort of correlation, autocorrelation based on the received signal, and then you take some decisions, okay? And what you're interested really, one of the most interesting parameters is this ASP, so the distance between two peaks of the received signal. So there are two colors here, if you see. There is a spectrum sensing, which is kind of light blue, and then green, which is transmission or reception. And this is the operation, so this is what you see from the radar, and this is how you operate as a cognitive radio, okay? So until you understand what's going on in terms of this ASP, you will keep sensing, okay? Once you have an understanding of that, then you will basically start to transmit, but you see that at the peak time you do still sensing to synchronize. You still want to track, right, the transmission of the radar. Otherwise you might be misaligned, and then it creates problem, because if you are not precise about this, you will start to interfere, right, to some extent. So you do have to keep track of the transmission of the radar and synchronize via sensing. Again, depending on the generosity of the database, you might get some information about this, but it could be, for example, the database is more limited in the willingness to share information, would just tell you the minimum and maximum value of ASP, and then you really have to find out the exact value from sensing, for example.
So this peaks actually, it comes when the radar is in the vicinity of the spectrum sensor. Radar is rotating.
Yes.
So let's say when it comes at the vicinity of the spectrum sensor,
Yes.
then these peaks come.
Yes.
So what happens when radar is not in the vicinity of
Well,
spectrum sensor?
it kind of decreases, right?
Yeah,
So
at least it detects, I mean, those are the things that is not in the vicinity of the spectrum sensor.
yeah, so basically, you know, it's really like you could make an analogy with somebody speaking to you. If the person is turning, like the sound fades a bit, right? And definitely you see it with you know, if you take measurements, I mean, you would see this, right? So when the radar is pointing at your receiver, you would pick up the maximum signal, and then you see that it's very regular, because the behavior of the radar in terms of transmission is very regular, right? So it does follow a regular pattern. They might not all be so clean, okay, so you do have different situations depending on the pattern. I think it was here.
Sir, in distributed sensing,
You see, this would be a circular radar, what I'm showing there, right?
sir, in distributed sensing,
Yep.
because since it's more of a a periodic sort of thing, or even if there's some element of correlation in terms of reception of pulse as well as the coverage.
Correct.
So in distributed sensing, can't we have this prediction sort of thing that two sensors are sensing
Yes.
and telling the person there's something about to come?
Yeah,
Because
yeah.
we know the geographical location.
Oh, definitely. Yeah, definitely.
Always
Yeah.
sensors can tell the next guy. And
Sure. Oh, totally. Yeah. I think honestly, if you ask me, a good area for investigation would be probably the MAC for the sensing in these bands, because I know. I mean, I did myself some work in the general context, but not in the radar bands. Okay, so I think this is kind of the infancy of the field. So any problem related with MAC design for sensing, good. Even protocols, honestly, of exchange to exchange information with the database. We didn't touch that. Okay, so that's definitely open, especially for somebody who is more interested maybe in the implementation, part and how to possible lead to standardization. These things are very relevant. I mean, yeah, just we didn't touch them. Okay, so just to give you some idea about the results, you find again this in the paper. So we do have a cognitive radio bandwidth of 20 megahertz. Again, this is just a parameter. You pick what you want. TW, which is the, let me just double check. Have many parameters. Double check this. Yeah, is the TW is the sensing window. So it's how much time you sense. And then you have a radar, which is, I think, this linear frequency modulation, if I'm not wrong, LFM, a pulse width of 28 microsecond, and a pulse repetition frequency of 1000. Again, I think this is reasonable numbers, but I mean, this is parametric, right? So you can change this. So by limited support, we mean practically for some parameters, but definitely not the intrapulse modulation, you do know some minimum and maximum values. For example, for the pulse width, for the pulse repetition frequency, for the antenna scan period, the database might tell you the maximum and minimum value. Okay, that's what we call limited support. The moderate support would be the actual values of this, so not the minimum or maximum. They tell you exactly the value, right? And the full support would be beside this. You would also know things like the scanning motion type, the intrapulse modulation, the antenna radiation pattern. So really, you know more or less everything about the radar transmission parameters. Okay. Again, these are arbitrary categories. You can define your own and have more. Doesn't matter. So the idea here is to show what changes in case you have this database assisted sensing approach. What changes if you increase the amount of information the database is willing to share with you, is willing to provide. So you see that actually here you have the basically three curves, right? They show the probability of detection. So in a sense, a curve that is on the right, it's worse than a curve that is on the left. Why? Because here it means you are less sensitive, right? To get a certain probability of detection, say of 90%, you would need to be above, say, minus 1, 2 dB. And for the moderate support case, maybe minus, say, 18. And then for the full support, maybe minus 22, more or less. So, of course, the more to the left you are in this figure, the better it is, because it means your system is more sensitive, right? It can pick the radar signal more efficiently. Now, if you consider the values we have been talking about before, I think they come from regulation. So, for example, to share the band of 5 gigahertz in the Wi-Fi context, they want your sensitivity to be minus 64 dBm, as far as I remember. So regardless of how much support you get from the database, if you get some, you're always going to do the job, right? You see? So basically, you're always going to be at a better sensitivity than the requirement. Okay? So no way you're going to have a misdetection. So just to tell that, you know, we are very, very conservative when we define these exclusion zones. So these, we are talking not peanuts, we are talking 40 dBm, okay? So it's a lot. And even more if you do assume collaboration, even of a limited kind. Let's say that doesn't matter too much in our experience whether you have a full support or some decent support. So if you know some parameters, even without knowing the waveform and so on, even without knowing the scanning motion type, you really just know, say, the pulse width and the antenna scan period, not much more than that. You get very close to the case where you have a lot more information, which means, you see, you are in a situation where you have a minus 120 dBm, so it's 60 dBm lower than what you are imposed to follow by the regulation. So that means, since you are so sensitive, you could easily shrink, right, the exclusion zone, because you don't need to be that protective, because your system is very good, right? So it will definitely pick up the radar signal. So you don't need to be, let's say, you introduce this safety margin, these exclusion zones, because you wouldn't trust too much the secondary system, right? Since sometimes they might miss the detection, then therefore let's put them far apart, right? That's the rationale behind the exclusion zone. But if your system is very good and almost never will commit a mistake in detecting your presence, you could have the guy as close as you want, as long as, of course, it shuts up when the radar is pointing in its direction, right? But potentially, you could really go very, very close. I'm going back to this point in a sec.
So typically, sir, full support means you're knowing virtually all the parameters of the classified signal. That in military scenario won't happen.
No.
It will never.
No, I agree, and that's why, you know, the interesting result here, there are two, I think. I agree with that. The moderate support, which implies probably not a lot of support, is pretty good. And even in the sloppy case of very limited support, you are still way below the sensitivity threshold. So that's good. Actually, I think this is the most interesting result. Not, you know, how far you can push to the left, but how far you can push to the right, in a sense, right? So we are definitely, I mean, our experience, we were a bit surprised, you know, by how far you are off. And we actually, there was a talk from a professor. He's an Indian professor, as far as I remember, Indian origin professor, and his name is Sumit Roy. He's working in Washington University, Washington, I mean, the state, Seattle. And he was talking about how conservative also FCC is in defining exclusion zones for radars in US. So this is a common problem. They're very, very conservative, okay? And you get situations like this, which is a nice picture that a student of mine drew. So this tells you how, now I don't exactly remember the two colors, but the message here is that if you follow the instructions in defining exclusion zones for radars in the coastal region, you basically exclude from communication most of the population in the United States. I think, I don't remember the ratio, but a lot. Because as you might know, a lot of the population in US lives on the coastline, right? So if you exclude that, probably you can maybe, you know, you would hinder the possibility for half of the population, something like this, okay? So there is a problem, it's acknowledged, okay, by a few people, and now there are some other issues related to this, like we have some work in not the sharing of necessarily radar bands, but sharing of incumbent spectrum in 3.5 gigahertz in US, can be radar, for example. And again, one suggestion is to have the the exclusion zone based on census tracts on population, and also that doesn't work. So the suggestions that are being made now by FCC or by Google, they are not really, they are poorly matching, okay, the reality of the transmission. So there is definitely room to improve this, okay, absolutely. So you know, if you're interested in this specifically, we have some other work, not on radar band specifically, but on this 3.5 gigahertz band, and there are some interesting results, okay, that show that you can do much better than the current framework or the current proposals. Also in this PCAST framework in US, what has been proposed doesn't seem to be really a very good idea, okay, so we do have some evidence for that. Now, you can, of course, I mean, we are talking about a secondary system which is fairly smart, right? Could be an LTE system. So why not using the capabilities we already have? Of course you would. So as you might know, already in 4G, MIMO is pretty much there, right? At least at the base station side you have multiple antennas. And one thing you can do if you have multiple antennas at the base station is to create directional transmission, right? Like beamforming. So for example, if you talk about exclusion zones, if you do nothing and you are within the exclusion zone, you cannot transmit. If you do nothing and you are outside of the exclusion zone, you can transmit. But these are dull cases. Okay, there's not much interesting going on here. Now the interesting case is whether you can transmit being inside the exclusion zone, and you can do that as long as you provide that when the radar is pointing at you, you create a null, right? If you create a null in your transmission, it means that electromagnetically you are invisible to the radar system, right? So in that event, I mean, of course, there's going to be some hardcore exclusion zone you cannot get close to, but you could potentially reduce the exclusion zone quite a lot. How much we're going to see in a second. Okay, of course, we still have database supporting the system. As you know, or you might know at least, the more antennas you have, the more capabilities you have in terms of processing available from the MIMO system. So for example, in the case of beamforming, the more antennas you devote to these, to creating these nulls, the more precise you can get. So for example, what we are showing here is that if you have, say, more than one antenna, you can start to actually cancel out, like to create nulls in multiple directions, okay? So in this work, we are assuming a single stream transmission. So out of NTX antennas, one will be devoted to the communication, and NTX minus one will be devoted to, up to NTX minus one will be devoted to this operation of cancelling some directions. Okay, so there is a trade-off, of course. If you want to focus on transmission, you get poorer in terms of nulling creation. So you get more interfering with the radar system. If you want to become more protective in terms of interference generated to the radar system, then you will have an impact on the throughput, right? So you cannot get both. So either you get a high throughput but you mess up with the radar, or you get a more moderate throughput but you also are more conservative in terms of protection towards the radar. And not only, I mean, the concern is not only the direct path, you also have multipath, right? So you do need to be careful about your transmission towards the radar, because it's not just line of sight, as we all, I guess, more or less all well know. Wireless is a lot about multipath, right? So if you do have clusters that reflect your transmission or deflect your transmission, this is as bad as this guy, right, for the radar, or this very bad. So you have to be careful also to cancel out some directions that have to do with the cluster scattering, right? What we came up with is an adaptive scheme, okay, that basically decides how many degrees of freedom it should use in terms of antennas to cancel out interference towards the, so it's more not cancelling out, it's more pre-coding, right? So you would avoid interference towards the radar. So it's like like when you say cancel interference, usually you mean at the receiver. Here we are acting at the transmitter, right? So it's more a pre-coding if you want. So if you are very close to the radar, of course you should be more conservative, right? And try to minimize as much as you can the interference you generate to the radar, and so on and so forth. If you're far enough, no need to do that. And you can use all of your antennas for communication, right? That makes sense, I think. And there are a couple of results I want to show you to conclude the lecture. So basically this is the interference to noise ratio versus the distance, right? So this is the interference you generate at the radar. And okay, couple of things. Of course, the more far away you are, the better it is, right? Because I mean, that's the spot loss decreasing. So at some point you will eventually get below a certain threshold you decide, right? So a very dull solution and simple one is just, you know, position your system far away, and then you do whatever you want. Now, if you want though to be smarter, you have to start to use the capabilities of beamforming, and of course, the more powerful your beamforming is, it means that the more you can avoid interference towards the radar. So not only maybe the line of sight, but also the reflection. So you start really to minimize quite a bit the interference, and you see that you really have a huge gap just with 4 antennas at the transmitter. So not a big MIMO system. You do go from something in the region of 70 here to something around 0 or 5. So huge decrease. And we are not talking about sci-fi massive MIMO stuff, okay? This is just state-of-the-art base station. I think actually 4 is not even that ambitious as a number. I think in LTE easily they go up to 8. LTE Advanced probably 16. 8 is definitely there, okay? So, and 4 is out there now, I think. So there is no, you know, this is just a way to use technology that is there to solve another problem, right? So another tip about your research is not necessarily that you do the revolution every time. Sometimes you just have to reuse techniques that are there for a different problem. That's perfectly fine, okay? That's still novel. Now, the other side of the story is that, of course, you are not just operating in the radar band for the sake of pleasing the radar system and keeping silent otherwise. You are doing it because you want to transmit your own traffic, right? So we are showing here what happens in terms of the throughput at the secondary system versus the distance. So again, it's a dual, right? So the more far away you are with respect to the radar, the higher the throughput you can get, right? Intuitive again. Why? Because practically, if you are far away, you have to worry less about interference to the radar. Therefore, you can use all of your antennas to do transmission rather than this interference prevention, right? Of course, if you are very close to the radar, then the situation is opposite, and you have to use many of your degrees of freedom in space to prevent interference, and therefore the throughput suffers. There are other things here, like we have a comparison with some ideal system not using beamforming. Doesn't matter too much, honestly. And then you would have an adaptive scheme which is kind of picky. So this would be the case where you don't adapt, right? You just use, say, 3 antennas to do interference prevention, 2 and so on. But what we proposed is also a scheme that adaptively picks the number of streams, the number of antennas you should use for interference prevention based on the distance. Very simple scheme, and it sort of writes the envelope, okay, to some extent, not completely, but so say this is, it does actually, because you have, so this is kind of a bound, so don't consider this purple line, but you know, the adaptive scheme, you see that basically is always on top of the envelope of the different possibilities, right? So it's like adaptive modulation encoding for those of you that are used to that. So you do have different modulation orders which are optimal at different SNR regions, and then the adaptive modulation encoding would simply write the envelope and always pick the best, and that's what we are doing here. A comment on again, topics of relevance to research. I think one big common theme for all well, modern communication systems, and 5G is no difference, actually even more so, it's adaptive schemes. So there has been a history of adaptive schemes in the past, like adaptive modulation encoding, adaptive MIMO in the precoder of LTE, for example, and many others. And so this is another example. So one good way to do research is also to understand how you can use this adaptive principle to your system. So you want systems that are not hard-coded in a sense. You want systems that are reactive to the situations, okay, whatever they are, and that's a good way to propose new things, okay. So yeah, so just a hint, you know, to look into these adaptive technologies. It's a good idea, I think. Okay. Good. Now, any question or comment? Yes, Ashwin.
There was a slide, the more antennas, the more cost you can consider.
Yes.
So in that slide you said that if apart from cancelling the line of sight component, we will also try to cancel the non-line of sight
Yes.
component. So how do you know that this where is the non-line of sight component, because you don't know the position of clusters in real scenarios.
Well, you don't and you do. I mean, in the sense that, you know, you of course have to have, I mean, yeah, in principle you don't, but, you know, you should then do, I mean, normally people are working on ray tracing, right? You know something. I mean, like if you are in a city or even in an outdoor space, in general countryside, there are some things that are bigger than others, right? There is a hill, there is a building, you know. For example, we are doing some study for massive MIMO, and we do adopt a deterministic channel model which assumes the knowledge of tall buildings in an urban space. Of course, if it changes the geometry, then you have to do the thing again. But the good thing about deterministic models is that once you know the environment, you are done with statistical like creative assumptions. So a problem with the statistical models is that they are very good as a general tool, right? And on average they give you some understanding, but this is not the real situation, and they might lead actually to complicated like problems. For example, what we are noticing with massive MIMO is that, you know, you do have issues with increase in the capacity. So if you do have like a probabilistic model, pretty much situations are always kind of nice, or like, you know, you do have a linear increase for a long period and so on, for a long range of antennas. But if you use a realistic model based on the actual geometry of the system, sometimes you get a saturation of the capacity very quickly, even with few antennas. So you basically have, you know, let's say in a single cell situation, single user MIMO, you would have a linear increase. If you have a probabilistic model, but if you have a deterministic model based on the geometry of the system, it's not true. You get a saturation, and the saturation might happen pretty quickly. So what I'm trying to say is that even if you have, say, 10 antennas, or if you have 50, it won't change that much. That's not the usual thing you get from probabilistic models. So there is a big component, I think, in wireless systems that have to do with the channel model. The default assumption is statistical. There is a reason for that. It's easy to track, and, you know, you might not have the possibility to do measurement campaign, but if you can integrate this knowledge with actual measurements, you know, and more realistic models based on ray tracing and other deterministic, you know, considerations, it's not a bad idea at all, okay? Because definitely the channel model and the modeling of things is very important. So you can as well spend time here to identify where the clusters are, right? And there are ways you can model this, okay? There are even works in the literature. Other example, I'm going back to this later in the course, we did study ultra-dense networks, okay? And we checked what happens if you have a single slope path loss model, which means one path loss exponent, and that's it, okay? Or if you have a probabilistic, like a more realistic situation where you have sometimes you're in line of sight, sometimes you're not, And just by changing this, okay, this is a very simple Bernoulli model for the channel. Either you are with the probability in line of sight or you are not with another probability. Complete different story, but really very different. So I'm going to go back to this, and the point here is that we spend so much time designing new techniques or many new things, in our system, and we normally forget that the basic we normally forget that the basic thing we have to deal with is the channel. Okay, so the channel is actually there is a reason why in many books and courses, very, very bad noise. To the point? No, I don't think so. Try to remove all sorts of interference. Okay, I'm almost done anyway. So there is a reason why in all your books, courses on wireless communication, you start from the channel. I think invariantly that's the case, right? And there is a reason, because that's the basic thing. That's the most common thing you have to face. That's the most important thing. So I think there has to be a lot of focus if you want to focus on research for 5G and so on the channel. Okay, the channel for new deployments, for new situations, for new technologies is as important as the technologies themselves. Okay, and in my experience, it plays a big role, and it does change.